All right, this is Ken Delcor. I'm going to do the last lecture on this particular Module 1 10 PowerPoint Intro to Heating. This one is particular, the lessons today are primarily on pressure and the use of certain instruments to be able to detect certain pressures within a heating system. So that's where we're going to start on this introduction to heating related to that. So in the previous lectures, we had kind of completed where we were looking at heat and heat flow and heat transfer. And this one is going to start this one will start particularly in the last section of the PowerPoint. So I'll use the PDF version of this as I take some notes here with you. All right, so the gentleman that is shown in this particular image here on this particular part of the notes, he's using an instrument. In this particular case, it's called an incline manometer, and he's using it to help measure some pressures within the system. And I guess the note that I would probably make in this one is, there we go. The note that I probably make in this particular one, I'm going to make this a little bit smaller, is how most of us, most of the service techs in the field, they're going to use, basically we use pressure to help us diagnose a system. As a general rule. And and to help diagnose the system, and I think specifically, I would say specifically we use it to diagnose what I would say is really to diagnose any type of air or gas pressure related issue. Any of those, it could be any of those that we deal with. So primarily that's normally what we do. I think one of the things that really helps to some extent when I think about these, it really helps when I go into a system and I start taking measurements. I think it really helps to kind of get a better feel for the system. I think that's usually one of the things that helps. You can almost think of it to some extent. We're kind of, let's say we're measuring the vital signs. If you use a medical, term, I guess to some extent, when you go in and you get your blood pressure checked, or you do this, or they're trying to get an idea of your vitals to some extent. And that's kind of what we're doing. We're using the vital signs to solve issues, to solve problems, and that's primarily how we would approach this one. So that's primarily what I would say. And this is only one example of it, obviously, that we're looking at specifically. Whether we're checking return pressure, supply pressure, gas pressure, whatever it might be, but it's a big part of what we do in our system. So let's expand a little bit more on that. So on the next slide on here, this is what I'm going to delve with in a little bit more with a particular handout that we have, and I also have another little PowerPoint. I'm going to go through a little bit on some of this. So, but as a kind of an entry point here to some extent, in the verbiage that's identified here, what we're showing is how we're identifying and saying our pressure is equal to our force per unit area is what we're identifying. So pressure is force per unit area. So let's talk about force and what exactly are they referring to. I think most of us think of pressure either in PSI, in inches of water column, in something related to that. So whether it's feet of water, if it's, there's so many different units of measuring pressure that we use in our field. Probably the most common is easily in inches of water column as well as PSI. So we'll start with PSI. So the way that this one was set up here on this particular slide is where you think of force as, how many pounds are we really referring to? So when we look at the density of water, and this particular one here, this water basically has a density of 62.4 pounds per cubic foot. So we're showing a foot by a foot by a foot. So 12 inches by 12 inches by 12 inches, and it's 62.4 pounds. So we consider that as, you might have heard me refer to that in the last lecture as the density of standard water. Now, of course, we know that that changes, but that's the standard density. Now, if we were to take that standard density and do a calculation where we say, okay, I want to take 62.4 pounds and the area that is sitting on that. So on a 1 foot by 1 foot or a 12 inch by 12 inch square, that would equate to 144 inches. So this basically, your 12 inches by 12 inches is equal to 144 inches squared. So that's where this square inch business right there is coming into play. So 62.4 pounds is the force that's sitting on a 12 by 12 square. Now, that 12 by 12 square that's carrying the entire weight. So the 144 square inches is really carrying all of the mass, all of the weight, all of the force of that water. So at 62.4 pounds divided by your 144, you're going to come up with roughly an equivalent, or a ratio in this case, of about 0.433 pounds per square inch. So let's say that's an equivalent that we typically deal with. Now, the thing that I want to point out to you, how pressure would be impacted to some extent, is if the force changes. So let's say the 62.4 pounds were to change. Now, that could be the weight of water, in a cubic foot. That could change that. If regardless of what it is, if the fluid becomes lighter, then let's say if I heat up water, it generally becomes lighter. So if I'm heating up water and it becomes lighter, as the warmer I make that, this 0.433 psi per square inch would certainly change. So we'll hit up a little bit on some more of those examples, and I'll go through a little bit more detail when I go through the other PowerPoint that defines pressure a little bit more on there. But I think this is a good starting point. Force per unit area is typically what we would certainly refer to as the norm, as the standard. So in this particular one. All right, so let's move on to the next one. So another feature of pressure. Now, the previous slide where we talked about pressure, and we're talking about the force per unit area. Now, why would this be important? There's a couple of reasons. One is it depends on how we're spreading out that force, how we're spreading out that weight. Whether it could be duct pressure accumulated, whether it could be pressure from you're hanging a unit, pressure on the floor, whatever it might be on a boiler, why there could be some excessive pressure, some sagging, whatever it might be. That would be an example of that. And I'll give a couple of examples here as we go through this. So specifically, when we look at the next slide here, which is referring to your solids. All right, so you might remember me talking about this in refrigeration. We made a point to say that when we have a solid, we expect it to push or to create all of the force in one direction. So as the arrows are showing here, that's creating all of that pressure. Now, why is that important? Why is that applicable? So why that's probably relative is the fact that when we are placing a furnace on a pad, or we're placing a boiler on a floor, as an example, and I'm going to just kind of show just a simple little area here to kind of identify that. So if, let's say, this represents my floor, and I place a furnace, actually, it's not my best work here. So let's say that this represents the base of some sort of a heating system. Now, the entire accumulated weight, that downward weight, that force, whatever that weight. So if this were a boiler, that could literally be, and some of these boilers, that could be 500 pounds or more of force. Now, on some of these boilers, they might have 4 legs. A leg there, or a little tiny base. And each one of those bases, let's say, happens to be, let's say it's 2 by 2. So each one of those bases is 4 inches squared. So that's a 2 by 2, 2 inch by 2 inch little plate, as an example. And let's say that there's 4 of those. So every one of these legs, this one, this one, this one, and this one, all has a leg. So we're literally looking at 16 square inches. Okay, now, the reason why a person has to consider this and at least figure this out is how in the world, whatever base that I'm putting some heavy piece of equipment on, or whether it's a dolly, or whether it's I'm trying to go down stairs, or whatever it might be, all of that force is going to be going directly down on whatever that surface area that you can do. And it's going to be all downward, as it would be in this case as identified in a solid. Now, if we were to use this, let's call it this equivalent of what was identified up in the previous image. We had pressure was equal to force per unit area. So that being said, if the force, or the pressure in this case, is 500, as an example, and that's certainly a heavy boiler. They make them heavier, and they certainly make them lighter. And if we were to divide that by the total of what this is sitting on, which is essentially, 16 inches squared, I now have a ratio of essentially 500 divided by the 16, which is coming out to about, in this case, about 31.25 pounds per square inch. Now, that may not seem like a ton of pressure, but whatever structure you're putting on, it's got to be able to handle that much pressure. Now, how do we handle that? What things can we do to help us to make this number smaller? Okay, so you might think of, the only way to make that number smaller is, you might say, I've got to somehow do something to change this. So if I make that bigger, stronger, where I can now take those 4 little legs and I can spread them out over a greater area, I can reduce the immediate pressure on a per square inch base. So that's kind of the one way that we could look at it. The example that sometimes I'll use, if a person were to go on, let's say if a person is trying to, if they're walking on a rubber roof, and they happen to have a stone in their shoe, and that stone is carrying a high percentage of your body weight, that stone has a lot of pressure at the immediate point of contact, which could puncture a roof or whatever it might be, or a screw. If you've got a screw in your shoe, that would be another example. There's many ways that we can kind of identify. I think everything relates back to this pressure of and the impact of really understanding our bases and understanding that when we're applying equipment, putting equipment in, that I have to make sure I am considering how much force, and do I have bases that are large enough that can carry all of that weight. So the more that that I happen to have, the greater the area I can spread that weight around, the better off I'm going to end up being on there. So that's kind of one of the things that's the point I would make. So bottom line is, as we know, in this particular area, we know that in this case the weight is distributed in one direction. For a solid. So that's the way I would probably describe that one. All right. Let's take a look at the next one. So the next one we happen to have, we've got water. And in this particular case here, now I like the water description. Now in my hydronics class, we have to learn a lot about water and the impact of water and how that really kind of matters to some extent. Now, the one thing to remember is fluids, and I would say this is with all fluids. So I'm just going to point this out. Is with basically all fluids, they basically will apply equal pressure in all directions. So all of these fluids will do that. Okay. All right, I guess I'm going to draw that line. I thought I was drawing a circle. Okay. All right, so they all will do this. So fluids will create a pressure in all directions. So they're showing an individual that is that's in this little boat. Now I want to point this out. Now this is not necessarily talking only about water. But we're also talking about gases, the air, the atmosphere. And in this particular case, what I want to point out is that this individual has the same air pressure on the back side of it as he does on the front side of it, as he does directly on top of him, within reason. So that's just our atmospheric pressure at that point. So when we think about that, why would it be any different for this one, for this guy? So we've got this guy that's his scuba diver. Now, I know from scuba diving that the further down I go, I have more fluid on top of me, and it creates more weight. So the pressure essentially is going to increase. But whether I'm a foot down in the water, or 10 feet, or 100 feet, or 130 feet, if I'm at any of those levels down in there, the pressure is the same all the way around me within reason. So that's really the point that I'm identifying in this particular case here. So whatever point that you are, that's really what it ends up showing. There's ratios that we use in our industry for water. For example, every time that I go roughly about approximately 34 feet. Every time there's a level of fluid that's approximately about 34 feet, that will be equivalent to approximately about 15 psi. It's equivalent to atmospheric pressure. A little bit about that as a rough idea. I'll talk more about that later and how that is when we're dealing with pressures later. All right. So in the next one, in the next slide here, we're going to take a look at just a couple of little examples on this. So, and these are going to relate to some of the handouts that I'm going to go through a little bit. And pressure is really one of those things that it's really hard to understand pressures. It's hard to understand really what they are, because it's, people measure it, but how much pressure is that really? And why does this happen? So we're going to do our best effort to try to get that going. Now, when you think about our atmospheric air, our atmospheric pressure, okay? So this would be, I'll just make a note of that this is essentially atmospheric All right. Now, this atmospheric pressure of approximately about 14.7 pounds per square inch, that's essentially due to the weight of all the air that's above us, from the outer atmosphere region all the way down to that, let's call it sea level, we'll say, is roughly about that. Now, what are those forces? So in this particular case, the forces are essentially, as you can see, the arrow is pushing down this way, it's pushing to the left, it's pushing to the right, it's pushing upward. It's essentially the same pressure all over. So it'd basically be saying, if I put my hand out in the air and I can see that, I don't have really a significantly lower pressure on below my hand than I do above my hand. Let's call it the same for the most part. That's just simple atmospheric pressure, atmospheric air. all of the air pressure that we are dealing with, excuse me, all of the air pressure that is around us is basically the same as that point. Higher in altitude we go, that will change. We'll talk more about that. The same thing goes with water. So my example that I had here, in liquids, we're placing it down, or these fluids we're placing it in those directions. Now, that means that, this particular scuba diver had pressure above, below, on the left side, to the right side, all those things. The same thing applies here. And that's really the point that we're trying to deal with. To expand a little bit more on this here. So we'll deal with, I guess the point that I'm going to make is this. So the further down, so the example that I made here is that, I have a certain level of molecules that are above this scale, and it's giving me a pressure of 14.7. Now, clearly that is atmospheric pressure on a gauge, is that my gauge, as you all know, would read 0. Now you wonder, and you guys know why. The gauge would read 0. Now, why would the gauge read 0? Well, when you zero out a gauge, you're kind of, they already zeroed out. They already zeroed at atmospheric air, because we kind of want to know, are we above, or are we below atmospheric pressure? That's primarily why it is. Even though that pressure exists, the gauge reads 0. Now, of course, that's with our, so we call that PSIG if it reads 0. The real pressure is 14.7 roughly, and that's PSI 8. So let's go to the Mercury Barometer. Let's talk a little bit about that. All right, now you might remember in refrigeration, we talked a little bit about on the impact and the benefit of a barometer and how that helps us. So a simple mercury barometer essentially has a glass tube that's filled up with mercury. And we take that mercury with, there's no air in it or anything like that, and we invert it into a little bucket. So we simply have a mercury tube. It's completely filled. We take that and we invert it. So we basically just flip it over, and then we put it into this little bucket, just like the image is describing right here. Now, the atmospheric air that surrounds this thing is going to push down. It's going to push down on the mercury. And so as the mercury is it's essentially a pressure difference between the mercury in the enclosed area in the barometer, which is on top, and the atmospheric pressure. So it's going to find that equilibrium to some extent. Now, in a mercury barometer, standard atmospheric air, we always say, is roughly about 29.92 inches of mercury. Now, that particular 29.92 in standard atmospheric pressure would mean that our barometer would be roughly about, from the difference from there all the way to there, would be roughly, let's call it 29.92 inches high, essentially is what it would be. And obviously, the changes in pressure will change the height of that. All right. So let's go to the next one here. Let's hit up on this one. So in this slide here, we're listing as our barometer, our pressure, showing the column of fluid that's roughly about 30 inches high. So we know that number is going to change. So we always say, the standard pressure is in that, as I had mentioned in the previous one, standard. There we go. And we typically talk about normal atmospheric pressure is 29.92 inches of mercury. Is typically, it's about 30. So the picture showing me 30, that's about what it ends up being. So you have to also understand, and you probably remember this, but it's a good review, is that we have roughly about 14.7 psi would also be equal, certainly would also be equal to the approximately mercury at 30 inches, it's 29.92. But it's also equal to, well, I'll put that down here, I guess. So it's equal to approximately about 29.92 inches of mercury. Or we could even say, we'll make it easier math, it's equal to approximately about 30. So about 30 inches. It's pretty close to that. So 29.92 in that area. So another equivalent that we would be dealing with typically, as I had mentioned earlier, it's also equal to approximately, I would say roughly about 34 feet. So if I made a barometer out of water, I'd have to have a barometer that would be about 34 feet tall to do the same thing. Obviously, mercury can be much smaller simply because it's so much heavier than water as a fluid. So that's primarily the reason why that is. All right, now if we expand a little bit further on this, is that on the next one that we're dealing with here, we have our atmospheric air as shown. Now, in refrigeration, we made references to the impact of atmospheric pressure on the pressure of our fluids and the pressure of air. And I think to some extent there are, if I'm at a higher altitude, there's less atmospheric substances, air that is above me. So when the fact that there's less, and there's, if you look at just the height from here to here as an example, the height from here to here as the example, that is, it's smaller, it's less, it's not as tall, so we would equate that to a lower pressure. And that, so again, you're going to have a lower pressure on those particular substances. So again, it's all about the molecules stacked. You go up in an airplane, and you know how they always talk about, hey, we have to pressurize the airplane. There's very few molecules. Again, very few molecules that are above, between the outer space and the atmosphere and where that is, and it's even a lower pressure. So it's really about that. Now, if you think about it, how does it relate to that? That same concept is exactly how we deal with the concept of whether it's water, whether it's air. The more molecules that we cram in that vertical height will relate to that. Again, I'll be going through this a little bit more with you to define some of these in a little more detail with you. All right, so upper and lower pressures. So we'll hit up on some of that. All right, let's take a look at this next one. So the next one, the next one is between dry air, moist air, and I want to use this a little bit to identify some of the concepts that we dealt with earlier. Now, it doesn't take a lot of pressure to make these changes or to make these adjustments. So let's hit up on some of this. So the first concept that we deal with here is that we say cold air is more dense, is one of the things that we say. Now, we got to ask ourselves why that is. And we're talking, if we're comparing cold air to dry air or cold air to warm air, and in both things being equal. In those situations, if cold air is more dense, one of the things that we'll generally associate with is that those molecules get really small. So if we have warm air, a molecule of the warm air maybe is this big. A molecule of the cooler air is maybe this big. We basically can pack a lot more molecules in a square inch or in a square foot or in a cubic foot. So it's essentially that's the reason why they say when you have the example you could use is, all right, I have a hot air balloon. If I warm up the air, why does that balloon rise? And it's simply about the displacing and being able to displace the mass or the weight of that fluid, or in this case, of air. Now, if I happen to have the one that's probably sometimes even a little bit more confusing to many people, and in some of the classes that we go through, we'll talk a little bit about the difference between dry air and moisture and where moisture goes within a system. And one of the examples that I oftentimes use is when we talk about we're saying dry air is more dense and moist air is less dense. So what that had to relate to is when we have dry air that's being a little bit more dense, that you got to ask yourself, okay, what's the difference between dry air and moist air? Now, if you have a cubic foot of air and some of the let's say the dry air or some of the dry air has absorbed or has one of the laws is the fact that air is essentially a mixture of dry air and moisture. And when you have completely dry air or air that is drier, some of the moisture some of the moisture has to displace in that same volume some of that space. So it's got to displace some of the dry air and take its place. And in that same square inch, square foot, cubic foot. And what has to happen now, so when we say, dry air is more dense, that tells you that air is very dense and dry air would tend to fall as a general rule, all things being equal. When we have moist air, so I'm going to use the example of, which is relative in heating systems, is when I have air that is very moist. And the question always becomes, what happens to that, that moist air? Why does it do this? And as a general rule, when you have air in a room, and you will generally find that the air, the dew point, which is a direct correlation to, let's call it, to the moisture content within the air. The more moist the air is, it tends to typically rise, is what it is. So, and I'll use the example of, and this is really evident, I've seen this in applications where you have somebody that's got a ceiling in their house, which that's pretty typical, people are going to have ceilings. And the question becomes, what happens to, where does the moisture go? Why are vapor barriers and things like that so important? So the more moisture just within a space, within this particular room, the more moisture, whatever moisture you have in a space, it typically wants to migrate, and it'll make its way up into these spaces, up in, let's say, into an attic. And so if that represents an attic, the question that I ask people is, well, do we ventilate attics? Why would vapor barriers be important? Or why are things like that relative to us? If we add humidity into a system, do we need to be careful about not putting too much humidity in that space? And are we going to create some issues with that? So even though we're dealing with very, very small differences in pressures, the fact of the matter is systems that are let's say, the more moisture you add into there, that moisture typically will rise up simply because of its lack of density. It's lower. So moisture typically rises and dry air typically falls down, is a typical rule. Now, commercially, this is what I ran into in applications on commercial jobs. So in commercial jobs, they typically would have a false ceiling that might be that could be, let's say, a bunch of 2x2 grills or 2x2 grates or 2x2 ceiling tiles, like you see in our classrooms. And what people would typically find is that when we would have issues with duct sweating, and we were look at the air up in that space and the air in this lower space, we noticed that the dew point was higher in the false ceiling than it was in the bottom part of this, and it was simply because of this fact. All right, and the next part of that, the next part of this thing is when we're looking at measuring pressures. So a couple of little things that I want to hit up on is the pressures. When we talk about measuring pressure, we deal with, generally what we're dealing with all gauge pressures as a general rule. And I think a couple of things that I want to point out in this one is, certainly I would say air pressures in a let's say in an air distribution system. In an air distribution system they can certainly be above or below atmospheric pressure. So that's a given. They can be above or they can be below. So that's something that we have to deal with. That also means, gas pressure is the same thing. So for example, in a I would say in heating equipment, in heating systems, I will say this, gas pressures can be above or below atmospheric pressure. And either one of those things, it's very possible. They can be above, they can be below. So for example, like a train, a train rooftop, we have rooftops that run, some of the rooftops that, they can run, negative, they can run basically like a negative 0.2 inches of water column, on up, and some of these they'll run the typical standard, 3.5 inches of water column, and that's positive. So we have ranges and that's for manifold pressures and those types of things. We have, there's a lot of variation there. So that's kind of the one thing. Again, we're dealing with above, we're dealing with below. We have gauge pressures, no different than even in refrigeration. You might remember there were times when we even had vacuums on our low pressure gauges. That we don't generally want to see that all the time, but that's some systems are going to run that way. So again, you just have to recognize it and realize that. All right. So the next slide, that's kind of just kind of dealing with basically just reiterating the point in refrigeration we dealt with pressures that were above and below atmospheric pressure. So if we were evacuating a system, we would be below atmospheric pressure, and you'll see how we have it zeroed out there. That's no different than in our heating systems. They simply are going to do very, very similar things. All right, so I want to talk a little bit more on some of these. So the next one, what are some of the pressures, some of the instruments that we're going to use for gas heating systems? And there's a few of them here. Some of them, the technology may have changed the looks of some of these. Some of these are still very relevant and very pertinent. It's definitely the case in most of these. So I would say, for example, there are some instruments that really do a good job of measuring very, very low pressure. So I would say the water manometer, without a doubt, the water manometer, water manometer. The water manometer is probably the typical instrument for measuring small pressures. In a heating system, I think so. So in all of these instruments that we're looking at, we have one is called a draft gauge, one of them is called a digital manometer, the other one's a differential pressure gauge, and a U-tube manometer. Every one of those things is very applicable. They're designed for measuring these small pressures on up. So those are fairly typical. Most of them, I would say this, most will read directly in, I would say, in inches of water column. So we'll call that, inches of W period, C period, inches of water column. So if you ever see that, that's what we're kind of dealing with on that. I think it's important, I think to some extent, the point that I want to make, they're not all equal. And you're going to see this when we deal with this in the lab activity, that we'll take a look and we'll just kind of, just to get a feel for like, how do I know if I'm picking the right instrument out? I think it's important to some extent to select instruments that can read accurately. And I think that's a big thing. So, within your system, you don't want to use, if you're measuring a tenth of an inch, a U-tube manometer is probably not the instrument to use. We have instruments that have certain scales and that are really designed for that. So we'll hit up on some of those types of things, and that's something that we can look at a little bit more specifically. So let's continue on. So in the next slide that we're looking at here, I'm showing water manometers, and these water manometers, the U-tube, the draft or slope gauges, what I call an incline manometer, they all have their purpose. And the incline manometer, I would say an incline manometer would do a much better job. So I would say this one, is definitely, I gotta do that. This one here, I would say would be really better for low pressures. The lower the pressure, I would say lower or small pressures. As a general rule. If I'm looking at, I would say, duct pressure, I could see that being a good application of it. I would say that would really be both of these two primarily. So duct pressure, I could see using that for, whether it's supply or return, either one of them would do the job on there. And to some extent, I'm going to say, or draft pressure. Now, the draft pressure would be like an event system, and that you can really have some tiny pressures there. Now, this instrument here, I would say would be more applicable to maybe to use it for certain types of gas pressure. Now, there are some downsides to using a U-tube manometer. So if I'm dealing with gas pressure, that would be one appropriate or applicable device. Now, the beauty of it is, it is fairly accurate. The accuracy doesn't really lie. It's old school, so definitely, it's kind of the standard of that, but it's only as good as you can read it. And that we have some issues with it. So one of the issues we have with that instrument is the fact that it has a fluid. So whether the fluid is water, we got some problems with that. Water freezes. So every time I go use it, I've got to add a little water to it. Or it evaporates or things like that. So we use a lot of digital gauges now that are more maybe easier to use. But again, it gives you a direct reading on these things, and that's primarily what it ends up being. So let's take a look at the next one. So how does a U-tube manometer? Again, we use this as kind of our, let's call it our gold standard. So when we ever question a manometer that we have, a gauge that we have, you could always go back to the old school method and figure out, okay, what's the difference in height and how does this work? What do I use for this thing? So if I were to use this instrument, there's a couple of things that I want to point out. So number one is you want to start out with that particular instrument zeroed out. So when they talk about it being zeroed out, what they're referring to is you got to find, in a U-tube manometer that's certainly going to be level or in this particular manner, you'll notice that it's all zeroed out. So the two columns are exactly the same height as it would in normal life, and we would be zeroed out. So wherever that point is, that's where it ends up being. Now these scales that you're referring to here, that's basically an inch. This is 2 inches. This one here is 1/2 of an inch. So it's an inch says an inch says an inch. So we could literally build one of these things as, it would be a good little activity really to see, is to take a 12-inch ruler and maybe use 6 inches as the starting point. 6 inches would become our zero. So basically you'd take let's say an 18-inch piece of tubing or 20-inch piece of tubing and wrap it right around the ruler. So this would basically be my ruler from top to bottom, and basically you'd have a tube and that would be attached on both sides of this, and then you just add some water. And so if you added water, eventually what would happen is that water would actually allow you to, it would essentially zero itself out as long as this is open to atmosphere and both sides of it. So we know that that's going to be zeroed out. So that's one of the things. And again, some transparent tube works awesome with this. It's really very, very good. So that's kind of the one way to do this. But it's the value of this is to really understand how much pressure does it really take to make an inch. And what I want everybody to understand is that there are applications where they'll identify something saying it's 3.5 or it's 1.7 inches, or we're going to run 0.2, or we'll have a pressure of 0.1 inches, whether it's positive or negative, and how low that really is, and why the selection of certain instruments is so important, so you understand, hey, if I grab something, is this appropriate or is this not appropriate? So I think that's the point that I would want to make on there. A lot of the newer electronic instruments, so for example, let me go back to this one up here. So a lot of people in the field really like the digital manometers. And the digital manometer, the beauty of that is of the, let's call it to some extent, the durability And it's available in such a wide range of so, some, I'll just make a note of that, some, I'll just say some opt for a digital manometer. Now, why they do that is I grab one scale, I don't have to worry about filling it up with water. All I have to do is make sure I got batteries that are good in it. It's got such a wide range. So that one instrument it might actually work fairly accurate for really low pressures, and it might work pretty good for pretty high pressures. But a person can always go back to the gold standard, which is essentially the YouTube manometer. All right. So this is something that in the lab that we want to give you the exposure to just to deal with, see what kind of pressures you're dealing with here. And in this particular one here, I'm just showing you how we're measuring gas pressure in a system. Now, whether this is a gas line, whether this is in a manifold, whatever it might be, it could be the supply line, whatever it might be. It's the difference in the columns of the fluids is what we're dealing with. So that's what I want you to recognize, is that we're looking at what is the height here and what is the height of the fluid here. So it's the difference between that. So whatever the pressure would end up being, what is the difference in the height from this point all the way to where it goes all the way across to this point. So just, for example, in this particular one, this instrument, I want to point this out to you that, let's say we're running, I think the image might be a little bit deceptive here. Based on what I can see here, in real life, if this were zeroed out and this manometer were to push it down 2 inches this way, then it would have no choice but to push it up to push it up 2 inches. Now you'll notice, when you look close enough at the scale here, it's probably looking closer to like 1.5 here, and it's probably looking here like, maybe 2.25 or so, which tells me that whenever this started, it wasn't really zeroed out. Now, again, maybe that's intentional in here to point that out. I think the point is that as you are using an instrument like this and you're looking at pressure, it's just simply, you just have to look at the difference between the two. So that's the key thing that I would point out here. So I'm going to put on here, the key is to read the difference in the columns of water, or water or mercury, I guess. But nobody's using mercury nowadays, so it's simply water is what it ends up being. So let's go to the next one. So in the next one, I'm just showing you a blower assembly. Now, in a situation like that, most blower assemblies that we deal with in our industry aren't going to read very high differential pressures. They're going to read some differential, but they're not going to read major differentials. So I could see this being part of a blower, in and out of a blower. And a couple of just notes that I would make on this is that in a blower system, this will be, I would say, the highest. Whoops, this will be the highest of the pressures. My screen is wanting to get crazy with me here. Highest pressures, and this will definitely be, that's going to be the lowest pressure. And that will be the lowest pressure. Highest pressure and lowest pressure. Now, again, reading this instrument, we're reading the difference. That's really what it is. So you have the higher of the pressures, which is showing on this side. It doesn't matter which side you use. It's just simply looking at the difference. So this time they put the positive on this side, and they put the negative or the lower of the pressures on that side. So one positive side of the pressure of the fan is pushing down, and the suction side of the fan is creating a negative pressure, and that's pulling the two up. So whether they would both be positive or whether they would both be negative, it wouldn't really matter. It's just simply what is the difference in pressure as they're identifying. And that's really what we have to kind of look at. All right, so The next one that we'll deal with here is called the incline manometer, or in this picture they're calling a slope gauge. This is what I would refer to as the inclined manometer. Now, oops. So it's an incline manometer. I think incline manometers I think they're generally very good for low pressures. I think it's really good. When we measure airflow in a system, we've got manometers that can read 1/4 of an inch and fractions of the 1/4 of an inch that are incline manometers. It's all in the way that they design them. This incline manometer, without a doubt, is really the gold standard when it comes to that, for the most part. For measuring air pressure, measuring duct pressures, it can be excellent. It is, but there are some issues, and one of the issues is, it has to be level. If this instrument were used and it would not be level, it would be inaccurate. It certainly would not work. So work correctly, it wouldn't read accurately. So that's kind of one of those. You got to use the right fluid as well. That's the other thing. So there are some of these instruments. I would say some are designed for water, and some are designed for. Some are actually designed for. I would say it's a specific oil fluid, and so we have this fluid that we use in our manometers that has a 0.28 specific gravity and a 0.28 specific gravity fluid, whereas if it were water it'd be 1.0. And you just have to know which fluid that you're using. You have to make sure you're using the right fluid. It's not the same. All right. The last couple here, and we'll hit up on, excuse me. The last couple that we have here, this one's just showing you another image showing you the, measuring gas pressure in a supply system. And we're showing it about 7.2 inches. Now I want to point out here, notice how they have 3.6 on that side, and notice how they have 3.6 on this side. So the difference in the two columns is essentially 7.2 inches. So you're just adding up the two columns, the difference in the column height. So that's really what it is. So even if you didn't start it at 0, you could still use the same thing on there. So it really works out well. Now, when we do this in the lab, one of the things that I want you to notice on here, and we'll go through some of these in the lab a little bit more, is the typical gas pressures. So I'm going to say normal. I'm going to say normal gas pressure. I'll just say supply pressure, normal gas pressure supply to the furnace, or to a unit, or to a furnace. Is typically about 7. It's only about 7 inches of water column is all it is. There. Water, W series, period. There we go. That's my typical normal amount. Now, I would say, and that's obviously for natural gas. So that's natural gas. Now, if this were LP, the typical, would be, probably I would say somewhere in that 12 inches of water column would be the norm to bring it to the unit. Now, I would say normal, we have some, in our lab, we're actually reducing it. Our normal main, I'm going to say normal main gas line in the BC 108 lab is 2 psi. Now, we'll have to hit up on a little bit of that. And some of the houses that are, they will also be 2 psi. If they run into gas pressure issues, they may have to bump it up. So there's in those particular cases, that manometer that's shown to the left, it would not be any good. This manometer on the left side would only be good up to about 8 inches. Anything beyond that, you're really pushing it. So typical, again, you have to be able to pick the right instrument on that. That's we have to do. So we have a normal main gas supply in the 108 lab at 2 psi. Then we regulate it. We drop it down. Down to a normal 7 inches or so, in that area. That's normally how we do that. Again, we're going to have you do this in a lab. And the last one. And the last one that we're going to be dealing with here is the last one we're going to be dealing with here is just showing, some of the typicals. And in the lab, some of the things that we'll kind of identify. So in this picture here, I want you to see this, that they're using this manometer to measure pressure on essentially a return duct. And notice how in this incline manometer, now we may have used a digital manometer, very likely, but the concept will be the same, is that the instrument is going to have one side open and the other side will be closed. Now when we select the instruments in the lab, we'll be able to see, we can show you exactly where that's at and what that's about. So the open side, that in this case would be the higher of the two pressures, so that would be the positive side. The negative side, because we expect that pressure to be negative, is actually going to be negative pressure in this return. Now, so being that the fan is drawing that air from your main system, your main duct systems, and they're drawing it through this application, we know that it's negative, it's negative, it's negative, it's a little more negative, and so on and so forth. And we're seeing this in this particular case as a direct reading of 0.3 inches. So it's really the difference between it zeroed out and 0.3 inches. Now, those are examples of certain pressures that we would deal with. So just to finish up here a little bit, in a real life system, it would not shock me to see 0.3 inches of water column here on a fairly good system. So I'd like to see in that, that 0.2 to, and this would be of course negative 0.2 to negative 0.3 would be, I would say, a very acceptable pressure in our systems. Leaving our furnaces, so I would say leaving, and this would be, before the, I would say before the cooling coil, I would say that we would expect to see somewhere in that positive, let's say, 0.3 to 0.4, which would be normal inches of water column. Now, what's interesting about this, and we'll talk about this when we get into the lab area, is the furnace manufacturers, they have their typical design type things, and when they're designing their systems, their equipment, they're typically designed essentially for heat only systems. They're designing it for a difference in pressure between here and here, that delta P. They're typically designing it for a heating only system to be roughly, about 0.2 inches of water column. And I would say with cooling, they're typically designing it for basically about 0.5 inches of water column. Now, what's interesting about that is that all of the tables are designed around that. All of the tables are, they're built around a 0.5 inch water column. So when you look at a lot of the tables, they're giving you what would be an appropriate CFM, assuming you're going to have a 0.5 inch of water column. Now, in a really, really very well-designed system, and if we deal with a 0.3 and we have a negative 0.2 into that blower assembly, we can make that with a cooling system. If the systems that are more restricted, you're going to see all of these numbers become more negative here, and they'll become more positive here. And that is going to be, that's going to be the issue that you're going to run into in real life. So I'm just going to make a note on that, is that restricted, whoops. Restricted will have, let's call it a higher positive pressure, and it'll become, let's call it a lower negative pressure. So it'll be more negative and higher positive, and you'll have a greater differential in there. Again, it's just talking a little bit about pressures and what we typically run into. So that will conclude this, and again, we'll reconvene and hit up on more of these to discuss some of these pressures that we're taking during